Okay, we are starting the recording of the model-free control and optimization lecture. Okay. Okay. Previously, we discussed the model-based reinforcement learning algorithms, and we said that the model of the environment is given, and we discussed the evaluation and the optimization of uh, the evaluation and the optimization technique for the model based. And in previous class, we discussed the evaluation. We started discussing the model free reinforcement learning algorithms. We discussed the evaluation of those evaluation of those evaluation techniques, and we talked about the offline and the online, and the offline being that the episodes have to terminate before we do the updates, and the online where we do the updates within the episode. Then in this lecture, we're going to talk about the optimization techniques, and we're going to make a distinction between the on policy and the off policy. A good example of the on policy is when a person is learning how to ride a bike, for instance. This person is learning from his or her good and bad moves to improve the skills. In this case, we say it's an on policy because the policy is learning from its steps. And this is as opposed to off policy. In this case, we have two policies. We have a target policy and a behavior policy. Let's go back to the riding example. And in the riding example, we can think of a person observing a second person riding a bike. So the second person is the behavior policy, where we are sampling and watching how the skills of riding a bike can be improved, while the person who is observing is the target policy. It takes the sample, those samples, and it improves in its own policies. All right, and we're going to talk on policy in this lecture, on policy control, on policy Monte-Carlo, on policy TD learning, and then off policy learning. Okay, so we did all of that in the earlier slide. Of course, the most interesting models in life are model-free. And when we say model-free, as we stated in the previous lecture, it's either the model's unknown, okay, or the model is known, but it is very complex, okay. And some example problems that can be modeled for NPD are listed here. In an on-policy Monte-Carlo control, we're gonna do a policy improvement and then a policy evaluation and improvement. But we shall see that we work over the action values instead of the state values, and the state values are used in the model-based MDPs versus the action values that are now will be used in the model-free. This you might notice this change in the algorithms, and this is, by the way, appropriate because it's easier to handle those actions as they come from sampled experience, okay, as opposed to compute the state values. Now, in the generalized policy iteration with the action value function, and we'll do the Monte Carlo approach first, where first we do a policy evaluation. Okay, so we pick up a scenario and we go all the way to the end, okay, and evaluate all these uh, rewards in the way to terminal states. We can do one or more than one scenario. Then we do a policy improvement. So policy evaluation, policy improvement, then policy evaluation, policy improvement, and continue this until we approach or we reach the optimum policy. Now, one thing what we'll do here is to discuss how we update this policy to reach to this optimization. What we will do is that we will use a epsilon greedy epsilon algorithm. An epsilon greedy algorithm, what it does is it specifies an epsilon value between 0 and 1, and this epsilon tells me that I am going to take a random action. So let's suppose, for example, in fact, I'm going to take a numerical example in my next slide here. Let's suppose I have this state, right? And I choose an epsilon of 0.9. And in other words, I'm going to take a random action 90% of the time. So the policy will be is that you will have 30% chance for everyone. Okay, so let's go back to this. So 30% chance for every action. Now the action with the maximum reward, what we will do, we will add to it 1 minus epsilon. Okay, so let's go back to our example here. And this example, what are the action values here? Here is -1, here is 3, and here is 0. So which action with the maximum action value? It is A2. Now, the policy then, what it does is, it will add to A2 1 minus epsilon. Epsilon is 0.9, and 1 minus will be 0.1. So, for the action from state 0 to A2, it will be added to it 0.1, right, which is 1 minus 0.9, and it, as a result, it will have 0.4. So the chances of action A2 taking is 0.4, A1 0.3, A3 is 0.3. And again, how we reach to these numbers, every one of them, since I have epsilon of 0.9, will take a point, will divide 0.9 divided by the number of actions, 3. So this takes 30%, this takes 30%, this takes 30%. Then I will look at the action with the maximum action value, which is A2 in this case, and I'm going to add to it 1 minus epsilon, which is 0.1. So A2 will be 0.3 plus 0.1, and therefore it will have a chance of 0.4. And that is how I improve the policy. I am biasing A2 because it has more action value. Okay, and then this algorithm basically talks about the steps that I just explained. You take an episode, right, and you go and compute those rewards and accumulate them, and then decide for every state where is that state with the maximum action value, and then update the policy, right, to be a greedy policy where you bias the action with the maximum action value. Okay. Okay, so in this epsilon greedy policy, as we stated, we go through evaluation, improvement, evaluation, improvement continuously until we reach the optimum policy. And we should mention that in the epsilon greedy policy, we have two fundamental things here working for us: the exploration and exploitation. The exploration is the randomness, right? And the exploitation, right, is taking the greedy action. I want to favor the action with the maximum reward. So I am doing both in this algorithm, exploring randomly, exploiting, meaning taking the action with the maximum rewards. Okay? All right. Now, how can I enhance this algorithm? Well, we can enhance this algorithm with multiple ways. One is we don't wait till the end of the episode, because if you look at the algorithm here, when I stated this algorithm, I have to go from uh, start state all the way to a terminal state. And this is an entire episode. Okay, that is that is the that is the main issue for Monte Carlo all Monte Carlo approaches, and this tend to increase the variance, and variance comes with noise. Okay, so what we will do is that we don't want to wait till the end of the episode. We use the newest information about the action value function and improve it quicker. And also, so here this approach lends itself to temporal difference TD approaches. In other words, update within the episode. And then we have decaying epsilon, right? Which means epsilon refers to the randomness, to the exploration, which means I will decay my exploration and rely more and more on exploitation, which makes sense. As you learn more about the environment, you get more information, more confidence in your actions. Okay. Now, on policy, Monte Carlo improve policy quicker. So one better way to start the policy improvement quicker, instead of waiting till the entire episode to complete, we can take few steps and then we do the improvement. The idea is to use the newest information about the action value, okay, as soon as possible. In other words, I don't need what this says. I don't need to complete the episode. I can do the improvement, the update a lot quicker, right, within the episode. If I accept the principle of updates within the episode, which temporal different it does, then I'm going to do the updates quicker. Okay. Now, we're going to talk also about the greedy in the limit with infinite exploration. Okay. This use decaying epsilon. So how do we, what's a decaying epsilon? We start with the epsilon referred also always to the randomness. We start with high value epsilon, but as I go through the exercise, I can decay this, in other words, reduce its values. And with reducing epsilons, we reduce randomness. So when I take too many number of all state action pairs are explored infinitely many times, and that means that this number, which represents visiting a state or taking a state and an action, sorry, this is number of taking in a state and action from a certain state, becomes an infinite, and then we can the policy really converges to a greedy policy, right? And an example of how we decay this epsilon is that we can make it 1 over k. 1 over k, it means one over the times that we visited that state. So here is what we'll do. We sample an episode, okay, for each state and action, right? We increase their number, right? And and the action is updated as follows. The updated action value gets the old one plus this. So this is like almost like my learning rate, okay, and the target minus the old value. Okay, now one thing here we can see is that we can improve we can improve the policy based on new action value function. So the epsilon here can be 1 over k, all right, and k increases across the simulation as the simulation or as the training goes on. And we can apply a greedy policy, but notice that this epsilon will be reduced, meaning the randomness will be reduced as we go through the simulation. So greedy in the limit exploration, Monte Carlo control converges to the optimal action value function. This is basically a theorem, but in brief, randomness decays with the number of training that we apply to the to the Markov decision here, Markov decision process. Okay. Right. Okay. Model-free on policy temporal difference learning. Of course, what we have discussed, the off policy, which is the Monte Carlo. The Monte Carlo versus temporal difference. Temporal difference has advantages compared to Monte Carlo, including lower variance. Lower variance, well, high variance associates with noise. Low variance means that low noise and better for stability and convergence. It's an online. It can take incomplete sequences. Okay, and the model or the main steps for TD, we just take a few steps, improve, update, and then take another few steps, improve, update. Okay, so it is much more lenient than the Monte Carlo, which requires a full episode. Okay, so the on-policy temporal difference learning, which is referred to as the SARSA algorithm. Basically what we do, we take an action from a state. There's this action. From the environment, we sample the reward, and we go to an action, a state S prime, and from S prime we take action A prime. Now it's important to notice that taking these actions from the states, taking action A from state S and taking action A prime from S prime is based on epsilon greedy policy. Okay, epsilon greedy policy. All right, so here we start with a state, we apply the epsilon greedy policy, right? All right, so from my policy here, I picked up action A. As I take action A, the environment tells me that, well, here is your reward, and we reach to state S prime. We apply the policy one more time, and we get action A prime. Now, once this is complete, now I go to the update. How do I do the update? According to the SARSA algorithm, and by the way, SARSA stands for state, action, reward, state, action. That is SARSA. The action value, the updated action value, which is this one, by the way, state and action. The updated, it's the old one plus the learning, the learning rate times the error. And the error in this case, target minus the old action value. And the target here is the reward plus the discounted action value S prime A prime. Okay, so now this is the new or the updated value of the action value, the old one, learning rate, reward, discount, the action value for S prime A prime minus the old action value, okay, which is this one. And by the way, you can rewrite this equation to be 1 minus alpha, okay, the old action value, plus the new, plus what we need to learn, the target that we need to learn. And this is the learning rate. This is the same equation as this one. Okay, we're just rearranging the terms to give a different meaning, a different perspective. So this the second equation, what tells me, I am keeping this old value and I am learning this value. Add these together and give the new value for the state action. This algorithm is referred to as SARSA, and continuously applying these updates will lead me to the optimum policy, which has the best action values. Okay, so this is the SARSA algorithm. We'll take steps, and from these steps we'll decide on determine S and A and the reward and S prime and A prime, and then they do the update value. Then move to the next state, okay, which is the S prime. Find out what and this is your action. Do the same thing again. Okay, so basically for next step, this S prime and A prime become your S and A. You have to find the new S prime and A prime, and update this equation. And magically, after doing this iteratively many times, you will reach to your optimum action values. Okay, so why it's on policy? Because we learn about policy pi from experience sample from pi. Okay, this is sampled by the same policy. Okay, right? We don't have a different policy. We no behavioral policy here. Okay, so this is basically another way of looking at the SARSA algorithm. It's a very famous Wendy grid world. We are moving from basically a start state to a goal here, and the agent can take any of the moves, right? Reward of -1 for each move results in an upward push by the wind indexed by the x-axis. Okay, so I have wind here, all right, and these winds are pushing me upwards, and these are the results in the upward push by the, and I'm gonna run this through the SARSA algorithm with discount of 1, okay, and once you do that, you will see that this is the optimum path here. Okay, this is the optimum path from start point to the goal here, or to the terminal. Okay, so the figure shows the optimum path computed by the SARSA algorithm. Also, figure displays the learning curve. So this is my learning curve. Okay, so these are time steps, and these are completed episodes, which is the y-axis. Okay, so the first episode took 2,000 time steps, right? Which is takes in the early stage of the learning. That's not surprising. The next episodes complete and learn faster. Okay, you can see this in this figure. Okay, so the point is early on in the learning, the first episodes they take more times to complete. Okay. You can much like we did in the evaluation, you can have n-step TD algorithm. Okay, and SARSA, since it's derived from TD, you can do the same thing, and it will impact your update equation. Okay, Also, you can look forward and backward views as we have done in the evaluation. I'm going to go over these quickly because these are really derivative of the main TD0 algorithm and the main SARSA algorithm. Okay, so they impact the update equation mainly. Okay, and this is another example on the SARSA. Okay, so we did the on policy, right? Let's go to the off policy here. And the off policy, we have a behavioral policy where we are taking sampling. Okay, so off policy learning, it learns and optimizes a policy, which is a target policy, independently of a followed policy, which is the behavioral policy. And it learns from experiences samples. So basically, I do have an environment, and I sample from the environment these experiences. Okay, and then I run those experiences, and we will see what are those experiences. And basically, here it is. This is the experience. The experience we mean state, okay, and action, okay, reward, okay, and a next state. Okay, so these samples, these experiences are saved in memory, and then we run our off policy algorithm, which is the Q learning, as we will indicate in the next slide. So the F policy updates, the Q values are updated based on the differences between discounted maximum value of the next state and the actual value. So the really, here is my update equation. You can see the update equation, reward maximum value of the discount times maximum value of the state S prime. So basically, and this is the main difference between it and SARSA. We will look at this state, right? What is the maximum action value? So let's say what has in the action, this action, this action, this action. We will take the maximum action value. We will add it to the reward. Okay, we'll discount it. Take the maximum action, we'll discount it. Maximum action value, we'll discount it with the gamma. And then we'll add to it the reward. This becomes my target, right? And I subtract the old reward, multiply it by the learning rate, add to it the old reward, and this is the update equation. If you compare it with the SARSA equation, right, with the SARSA equation, instead of taking the next state, next action, S prime, A prime, we are taking the maximum. So we're not following a specific action as in SARSA. We are taking the maximum action of S prime. Okay, that's the main difference in the algorithm. Okay, so this is more on the differences between on policy and off policy. On policy, policy learns from itself, like a person learning from his or her experiences to improve his or her riding the bike. And off policy, it means I have somebody is watching another person to improve his or her own skills of riding a bike. So the person who is being watched is the behavior policy. The person who is watching is the target policy. Okay, and the off policy, because we really don't need to complete episodes here. We are doing within the episode updates. Okay, right. So this is basically what we mentioned earlier. So once we adapt this equation, this becomes now my Q learning algorithm. And in a nutshell, the Q learning algorithm, we will keep going through these states as we have done before, but instead of moving from a state to a state as we have in SARSA, I'm going to have these experiences stored in memory and then load them one by one and then apply them in my Q learning algorithm. And the reason well, somebody might say, well, why don't I just go from S to A and S prime to A prime? And here's the answer is that I don't have an A prime in the Q learning. In the Q learning, I don't follow a S prime doesn't go to any specific action. We take the maximum action. And that's why once we do the update here, okay, I go and load up another experience with which shows me a state with its action reward to the next state, and then I will take the maximum action of the next state, do the update, okay, and then go for another experience. Okay, so the idea is that I'm loading up these experiences one by one because supposedly they have been sampled by some other policy, and I'm using them by some other behavior policy, and I'm using them to improve my target policy. Okay. So if we look at the differences between SARSA and Q-learning, the main thing here in the update equation, okay, that's the main thing. Look at the update equation in SARSA. It is using this target is from the policy itself. But here they are sampled from somewhere else, okay? And once I do the update, I can move on to the next state and to the next action, right? Here I can do to the next state, or I can sample, I can load up another sample, to be honest, okay? All right, so these the update equation stands out are the main differences between the SARSA and the Q algorithm. With that, the other slides are kind of more information for you. I conclude my session here where what we did in this lecture, we explained the optimization technique, right, using on policy, right, mainly SARSA algorithm, and using off policy, meaning mainly the Q learning algorithm. And thank you very much for your listening. We're gonna take a Q learning algorithm example in our next class. Bye-bye.